Ladies and gentlemen, we continue our work in Chapter 6 on analytical geometry with the first of the many conic sections, circles. This is conic sections, and we are dealing with one of those conic sections, circles. We learned in the last video that all circles can be defined with a general equation, x minus h squared plus y minus k squared equals r squared. This formula looks very much like the distance formula and comes directly from the Pythagorean theorem. Now h and k in this formula represent the center of the circle. X and y represents any point at all on the circle, and r represents the length in between those 2 points. All you need for a circle is a center and a radius, and you can define any circle. So let's take a look at some example problems using this formula. Find the center and radius of each circle. So part A is very easy. For part A, the equation given looks very similar to the general form of the circle equation. So for number A, or letter A rather, the center is pretty easy. You can just look at it and recognize that the center is 3, -7. And then the radius is going to be the square root of 19. Not 19, but the square root of 19. Again, this didn't take any work. Once you recognize that you are dealing with a circle equation, you can just look at it and take information from it. This is sort of like way back when we first learned about lines. We learned that there are linear equations. When a linear equation is written like this, it's really easy to know right away that the slope is 3 and the y-intercept is 5. This is called slope-intercept form. It's just one way of writing this particular equation. We could have written this equation many ways, though, and the slope and the y-intercept would not have been as obvious. For instance, the same line could be represented by this equation, 6y minus 2x over 3 is equal to 5. This equation, if you were to graph it, would give you the exact same line as the other equation. It's not as obvious looking at this equation what the slope is. If I just gave you this equation and asked you, well, what's the slope? It's really not obvious right away that the slope is 3, and it might not be obvious that the y-intercept is 5. So the way that a equation is presented can make it easier to take information away from that equation. So that takes us to letter B. We are given an equation that does not look like a standard form equation for a circle. However, we are told it is a circle. I can verify it's a circle by going to a website here, Wolfram Alpha, and putting the equation into the equation bar. This is just like it's written. And let's see what it gives me. This website knows how to deal with any type of equation. So, sure enough, it gives me a graph of a circle. It looks like the circle is right around, I don't know what that is, maybe 3, -2 or something like that. But more importantly, down here, it gives me alternative forms of the same equation. So these 3 equations here, here, and here all are different ways of writing the equation up at the top here. The one that looks most like the form that we learned about in the last video is this first one. From here, all we'd have to do is move this 25 over to the other side, and it would be pretty clear that the center is 3, -2, just like I guessed, and the radius is 5. Now, if we look at the equation as it's given, it's really not immediately clear that the center is going to be 3, -2, or whatever it was. Our goal then is to rewrite this equation so that it looks more like one of these equations. If I could rewrite this guy so it looks like this guy, then I will be able to just look at it and know the center and know the radius. So the process we're going to use to do this is a process that we dealt with earlier this year when we were dealing with parabolas. It's called completing the square. You saw this earlier in the year dealing with quadratics. So for instance, here's a quadratic. Y equals x squared plus 6x plus 10, something like this. So when a quadratic is written like this, it's really not clear at all what the graph is going to look like. I know that quadratics are parabolas, but I have no idea like where the x-intercepts are, where the vertex is, or anything like this. So we use a process called completing the square. Here is the basic gist of it. We want to rewrite this thing. I'm going to take, and hopefully this process looks familiar to you. I'm not going to go into real detail about where this process comes from. I'm just going to give you the steps for now. I take this middle term and I add 9 to it. And the plus 10 just comes right down. And if I add 9 to the right side of the equation, I also add 9 to the other side of the equation. So I've added 9 to both sides. What is the purpose of doing that? When I add 9 to this expression right here, what I'm left with is a perfect square trinomial. That thing is factorable. If I were to rewrite it now, the left side, 9 plus y, but this x squared plus 6x plus 9, that is factorable. It's x plus 3 times x plus 3. And if you do it right, you'll have a repeat factor every time. X plus 3 times x plus 3, it means the same thing as x plus 3 squared. This is why it's called completing the square. It was only the number 9 that was going to allow us to rewrite this formula this way. I can then move the 9 back over, and I've changed the look of the equation without actually changing the value of the equation. Subtract 9 from both sides. When you rewrite a quadratic by completing the square, it tells you the vertex. This is called vertex form. And now I at least know something about this parabola. This vertex would be at negative 3, 1, the point negative 3, 1. The process for taking on the circle equation above is identical. We are going to rewrite this equation, except we are going to complete the square not once, but twice. We're going to do it once for x, and we're going to do it once for y. So let's take another look at this equation down here. We are going to rewrite this. This is the same equation that was above in part B. In order to complete the square, to rewrite the equation, first thing I'd like to do is group all the x stuff together. So I get the x squared and the 6x together. I am going to leave a little gap there because I'm going to end up completing that square. I'm also going to write the group the y stuff together. I'm going to leave a gap there too because I'm going to end up writing something in that little gap. The 12, I don't really need the 12. I'm just going to move it on over. It's just in the way right now. So the goal is to come up with two perfect square trinomials, one that deals with x and one that deals with y. The process for defining these perfect square trinomials is the same each time. You take a look at the middle term and you split it in half, negative 3, and you square it. And that's what you add. If I add it to the left side, I must add it to the right side to maintain equality. The y portion of this equation works the same way. Take half of 4 and square it. You get 4. 2 squared is 4. I must add 4 to the other side. Now that it's written, now that these underlined parts are perfect square trinomials, that was really hard to say. Now I can factor it. X minus 3 times x minus 3. You can confirm that x minus 3 times x minus 3 gets you x squared minus 6x plus 9 just by FOILing, distributing it. I'm not going to do that right now, though. So y plus 2, y plus 2. If you factor it, and get two factors that aren't the exact same, then you did not complete the square. You completed maybe a rectangle, but you did not complete a square. Might as well combine these guys. This is kind of like all the leftover scraps, but these numbers together are going to come together and make the radius over there, because that is part of the formula. X minus 3 times itself means x minus 3 squared. Y plus 2 times itself means y plus 2 squared. And now I have 25 there. If we compare this to the formula, the general formula, well, it's pretty much identical now. X minus h squared, y minus k squared equals r squared. Now the center and radius should be pretty clear. The center of this particular problem equation is 3, negative 2. You always work with the opposite sign, the opposite number, because the equation has negative signs built right into it. The r, then, the radius in this problem, is in fact 5. This is not r. This is r squared. So the radius is 5. And sure enough, if you graph that thing, you get this thing. Positive 3, negative 2 with a radius of 5. This equation represents that graph. That's all. Goodbye.